In this video, we're going to introduce the idea of game theory. We'll talk about simultaneous games and repeated games. And in the next video, I hope to talk about sequential games and repeated sequential games. We'll start off this video by taking a look at a clip from one of my favorite movies, The Dark Knight.
Sir, they've stopped their engines.
Right, get on the radio. Tell them we'll come back and pick them up once we dump the scumbags.
Liberty, this is Spirit. Come in.
What the heck was that?
Liberty, come in, please. This is Spirit. Come in.
Get down to the engine room now.
Captain, got 100 barrels down there rigged to blow. In this.
Oh my God.
Looks like some kind of detonator.
Why would they give us the detonator to our own bomb?
Tonight you're all gonna be a part of a social experiment. I'll blow you all sky high.
Liberty, come in, over.
It's dead.
Anyone attempts to get off their boat, you all die. Each of you has a remote. Blow up the other boat. At midnight, I blow you all up. If, however, one of you presses the button, I'll let that boat live. So, who's it gonna be? Harvey Dent's most wanted scumbag collection, or the sweet and innocent civilians? You choose. Oh, and you might want to decide quickly, because the people on the other boat may not be quite so noble.
Stay back.
Well, now, who are you to decide? We ought to talk this over, at least.
You don't all have to die. Those men had their chance.
We are not going to talk about this.
Why aren't we talking about it?
They're talking over the same exact thing on the other boat.
So, what should the passengers on the respective ferries do? Right, down here we have the criminal ferry, and up here we have the passenger ferry, and we're going to create a decision matrix. Both ferries can choose to either wait or push the button. Right? So down here the criminals have the choice wait, choice push the button, and up here the passengers have the choice to wait or the choice to push the button. In each of these four boxes we're going to put their payoffs. So the number on the left corresponds to player number 1, and the number on the right corresponds to player number 2. So player number 1 in this case is going to be our criminals, and player number 2 will be our passengers. If they both wait, their payoffs are negative 75. We can go ahead and fill out the rest of this decision matrix. We're going to go through how a game theorist would solve this and decide what the best course of action is for each person. So we'll start by going through the mind of the criminals. So the criminals have two options: they can wait or push the button, and the passengers have two options: they can wait and push the button also. So what the criminals need to do is think about what their best course of action is depending on what the passengers do. If the passengers wait, we're in this column, and the criminals can choose to wait with an expected value of minus 75, or they can push the button where the expected value is 0. So if you could have negative 75 or 0, you would choose 0. The criminals would too. Okay. Now over here, if the passengers push the button, your best course of action would be wait, where you get minus 100, or push the button, where you also get minus 100. Well, you're indifferent between the two, so it doesn't really matter. So these matrices can get bigger, so to denote indifference, I usually put a tick mark by the ones you're indifferent between. So these are your best responses. So the criminal should always push the button, right? You can see down here, wait is your dominant strategy here. Boom, you always want to push the button. You never want to wait if the passengers are waiting. And if the passengers are pushing the button, you're indifferent between the two. So you would prefer to push the button than to wait. So your dominant strategy, you should always push the button if you're criminals. Now let's move on to the passengers. What should the passengers do? Well, we'll do the same thing, but we'll look at what the criminals would do in terms of what the passengers should do. So again, we're going to look at the best responses for the passengers in terms of what the criminals are going to do. So if the criminals wait, the passengers can get minus 75, or they can get 0, and you would prefer 0 over minus 75, so you're going to want to be over here with the push button. Okay? And now if we go down to push button, the passengers can get minus 100 or they can get minus 100. So they're indifferent because minus 100 is the same in both responses, right? You can wait and get minus 100, or you can push the button and get minus 100. So that means they're indifferent. So if they're in this column for wait, or they could be in this column for push the button. Push button is going to be the dominant strategy here because you have a 0, which is underlined, and the minus 100, which has a tick mark by it. So you want to be in the push button. Since they both have dominant strategies, we can come to a Nash equilibrium, and our Nash equilibrium is going to be down here at minus 100, minus 100. Both ferries should be pushing the button. I won't ruin the movie for you. If you haven't seen it, check out the Dark Knight trilogy. Pretty good Batman films. So since we're talking about game theory, we should go over kind of the general outlook of what game theory is. Basically, you have 3 vocabulary words you need to remember. There are rules, which are all the actions that are allowed in a game. There are strategies, which are the plans of actions the players can take. In the ferry example, the criminals' possible strategies were wait or push the button, and the passengers' possible strategies were wait or push the button. Then the payoffs are your rewards for your particular actions. So the payoffs were the actual number values that were given to each of the players. Now we've looked at an example of a game with a dominant strategy, and now let's look at an example of a game with a mixed strategy. Both rock, paper, scissors, and if you think about soccer, a penalty kick has a mixed strategy outcome. We'll start by looking at soccer here and a penalty kick. So down here we have the shooter and the keeper, and the shooter has to choose whether he wants to shoot to the left or to the right, and the keeper has to choose whether he wants to dive to the left or to the right. Okay? So we'll go through this just like we went through the other matrix, right? If you're the shooter, you're going to think in terms of what the keeper is going to do. So if the keeper jumps to the left, your potential odds are 0.1 or 0.45, and you would much rather have 0.45 goals than 0.1 goals, right? So you have a 45% chance if you shoot to the right and the keeper jumps to the left. Now, if the keeper jumps to the right, you can shoot to the left or shoot to the right. And if you shoot to the left, you have an 85% chance of scoring. And if you shoot to the right, you have a 20% chance of scoring. So you would prefer to shoot to the left. So in this case, you do not have a dominant strategy, right? If he jumps left, you want to go right. And if he goes right, you want to go left. So there's no dominant strategy for you here. Now, in terms of the keeper, you need to think which way minimizes your expected goals given up. So if the shooter shoots to the left, do you want to jump to the left or to the right? Well, you want to jump to the left. Because minus 0.1 is greater than minus 0.85. So you're giving up less expected goals. Now, if the shooter jumps to the right, you're going to compare minus 0.45 and minus 0.02. And minus 0.45 is less than minus 0.2. So you would prefer to jump to the right. It gives you a better chance of blocking his shot or him missing. So there's a mixed strategy here. Okay? The shooter doesn't have a dominant strategy. He doesn't always want to go left or always want to go right. He wants to mix it up. And the keeper is the same way. He doesn't know which way the shooter is going to go, so he wants to mix it up also. So the last 2 examples we looked at were both one-shot games. Now we're going to talk about repeated games. If you think about 2 gas stations next to each other, they have a repeated game every day where they set the price in the morning, and people choose which gas they want to buy based on the prices that are advertised out in front of the gas stations, right? So down here we have 2 gas stations. One is selling gas for $2.19, and the other one's $1.95. But let's think about them in terms of a game, okay? So down here, we have the same decision matrix. We have the Speedway and the Shell Station. The Speedway can set their price low or high, and the Shell Station can do the same. They can go low or high. And here's our payoffs. If they both set their price low, they're both going to get 200 for their payout. If Speedway sets their price high and Shell sets their price low, Speedway is going to get 50 and Shell will get 550. And if they both set their price high, Speedway and Shell both get 400. Okay? So let's see what each group should do. What should Speedway do if Shell sets its price low? Do they want 200 or 50? Well, 200 is greater than 50, so they're going to go with 200. And what should Speedway do if Shell sets its price high? They can get 550 or 400. Well, 550 is more than 400, so they should set their price low again. So because Speedway would like to go low when Shell sets its price low and high, we can say again that Speedway has a dominant strategy. Speedway should always set its price low. That's its dominant strategy. Now we can look at the Shell Station. What should Shell do if Speedway sets its price low? Well, they can get 200 or they can claim 50. 200 is more than 50, so Shell should set its price low. What should Shell do if Speedway sets its price high? They can get 550 or they can get 400. 550 is more than 400, so again, Shell should set its price low. So Shell also has a dominant strategy of setting a low price, which leads us to this Nash equilibrium here, 200 and 200, right? But if you notice down here, we can get 400 and 400, and that would make both groups better off, right? If Speedway and Shell were able to both set their prices high, we could be down here at 400, 400 instead of 200, 200. A way they can do that is called a commitment strategy. So a commitment strategy means that Speedway and Shell get together and they both say, hey, we're going to set our prices higher than we would otherwise. And they both agree that instead of them both charging $1.95, they could both charge $2.19, and then they will split that higher revenue. So if they use a commitment strategy, they could end up down here where they both set prices high. The problem with commitment strategy is one of the groups could decide to screw the other group over. So Speedway sets its price high, Shell could set its price low and actually capture more of the market over here, as we can see. And the way to deter that is called tit for tat. And all that tit for tat means is if Shell sets its price low, then Speedway will set its price low the next round. Okay? So then we're just stuck back here in our purple equilibrium. Whereas if we stayed with our commitment strategy, we could stay in this yellow equilibrium. The goal of a lot of regulation is to prevent companies doing this. A lot of our antitrust and oligopoly regulations prevent cartels and other groups from artificially inflating prices when they should be down here in the purple and they go over here to the yellow.